After
We're not getting the people in
26.
the room.
After 26.
Yeah.
It's recording.
From the
I don't know then what's going to happen in the exam then. Exam you cannot have 5 people.
okay, I told you
Online. You have it online.
it's gotta be online. I hope, inshallah.
Ah, yeah. Okay, that's better.
Not contradicting doctor. I hate this software so much. It's very bad software.
Good attempts?
Yeah.
So then pray that everything is solved. Okay, recording? Okay. Bismillahirrahmanirrahim. Guys, so recall me what we did for AM double sideband suppressed carrier. What happened in the modulator? You had your message and then multiplied with
The
carrier, which gave you your AM double sideband suppressed carrier. That means no carrier because there is no DC, right? Remember? Good. And we saw that when we do it in frequency domain, because of multiplying with carrier, the signal is shifted to very high frequency, right? We saw it, right? Good. Now in demodulated side, how can you get your signal back? Sorry? Sorry? Multiply again, good, by same.
Carrier.
This is the catch, huh? Same. When you mean same, that means same in frequency, same in amplitude, same in phase. Even if there is small phase difference, you will not get your exact signal. You understand? And over here, huh? You have low pass filter. Rectifier is for with carrier because you want to get the positive part. When you have double sideband suppressed carrier, just multiply and low pass filter. The best way to know why you need a low pass filter is if you just multiply AM with cosine omega CT, you will see that at the end you have half M1 plus high frequency component.
The rectifier was when there was DC.
When there was DC, yeah. So in the exam this can be asked, okay? Why are you, explain why you do this. So what you should do is, you multiply, you get the signal here, which is just math, right? Your AM signal, which you got from here, what is your AM signal? Message multiplied with cosine, and then again multiplied with cosine, okay? And if you do the math properly, so this is like M1 cosine square omega CT, right? Right? So that's M1, what is cosine square omega CT? Sorry? Half, okay, half is there, then?
Trigonometric formula.
Exactly.
Are not our strongest suit, doctor.
No, that's a big difference between a technician and you. You know the math and the analysis.
I know.
This is why there's a
I know
difference
it.
between CNAQ and this.
I know it, but I need to see the formula.
So cos A cos B is cos A plus B plus cos A minus B. Okay? You can check. Always this is easy. Cos A plus B is easy. Cos A, cos B plus, if this is plus, this is minus. Sin A, sin B plus cos A, cos B plus sin A, sin B. So this goes, and that's, so it's actually half. Half. Is it half? No, it's 2, sorry. Okay? If you do the same thing here, it's omega C, so it's like this. Cos omega CT, cos omega CT, right? So that means if I make it, so this is what I want, right? So half cosine 2 omega CT plus 1. Make sense? So, and then this is half M1 plus half M1 cosine 2 omega CT. So this is your low frequency signal, and this is your high frequency signal, right? So once you do a low pass filter, this goes away. So you're left with only this. Okay? Good.
Doctor, could you ask me an example to do the math?
Of course, yes.
But you will provide it with the trigonometric formulas.
If it is, I can tell it to you with a penalty. Okay?
With a penalty?
Yeah.
Doctor,
Because there is only 3 trigonometry formulas: sine a plus b, cosine a plus b. If you know sine a plus b, then you eventually know sine a minus b. So these are only 2. Only 2. I think this is very easy for you to remember. Okay? Sine a plus b is sine a cos b plus cos a sine b. So what will be a minus b? Just minus here. Cos a plus b is cos a cos b minus sine a sine b. Okay? Okay, I'll give it to you, don't worry. Okay. Okay, and the output is scaled M1. Clear? This is clear, right?
Scaled.
Everybody is understanding
Scaled by
this.
half, Doctor.
Huh?
Scaled by half.
I will always say K because sometimes
Because-
when you have QAM, it is not half, it's 1/4. So it's better to say K, which is a scale. So in other words, it's a scale. That's it.
Doctor, why can't we just use an amplifier and like compensate
Yeah.
for the
So good, you can say a low pass filter plus
amplifier?
amplifier is M1. Good. But let's make it simple.
Okay.
So if I ask you how can you improve it, you say you use an amplifier, right? Obviously, if this one has a phase shift, suppose this one is cosine omega ct and this one is cosine omega ct plus phi, right? So I will not have M1, I will have M1 phi, right? So how can I solve it? Use a phase shifter. Okay? Right? Yeah.
Does it matter if I use it after the low pass filter?
No, of course it matters. Yes. Stop corners doing it. Yeah, that's a very good question. Do the math. How can you, if it now over here, it's in the multiplication terms, right? So how will you,
Is it in the multiplication terms?
yeah, it will be in the multiplication terms.
Okay, then,
How can you, you have to divide.
but what will it be in this? So there will be no phase shift?
If there is a phase shifter here, if you do the math, you will get something like this, KM15. So he's telling why don't we do it over here, the phase shifter.
Okay.
But phase shifter is like removing the phase, right? How can you remove the phase here? It's a multiplication term. If you want to remove 5 from here, what should you do? Divide by 5. You cannot do minus 5. Can you do minus 5? How can I remove this? If I tell you remove this 5, what will you do?
Multiply it with 1 over 5.
If you have to remove this 5,
Multiply by 1 over 5.
you have to multiply by 1 over 5. Right?
Okay, amplifier.
Amplifier, okay, amplifier, then you have to find phi. It's much more complicated.
But you can find K.
You can find K?
Yeah.
Oh, that's I actually don't have to find K. This is why I'm putting K M1. This is why I'm not putting the amplifier.
Okay, Doctor.
Why you don't need to
Doctor,
find K?
if we
One by one. Let me finish with him.
Okay, yeah.
Why you don't need to find K?
Why I don't? At the end, I told you, right? If the amplitude is like half throughout, it's not a problem.
Okay, so the phase shift and the K, we can make it one.
A constant.
Yeah.
Oh, okay. Okay. K15 becomes K. Something like this. Okay, that's.
And doctor, we also have another thing. Okay, doctor, we know the amplitude of the signal method, and we know the method of demodulation.
Mhm.
And if we know that it's gonna be half, then it's gonna be half multiplied by phi is gonna equal to this k. So we can easily find what pi is.
What phi is?
Yeah.
And then do the amplification. Okay. Now I understand what your point is. Yes. Yeah. Yeah. Okay. That's a very good. That's a very good thought. You can, like, if this question comes, you can say that, right? But this, because we are looking at a general formula, we will do this for the QAM. In QAM, we won't have KM15. We have, because of this phase difference, we will have M2. A second. We'll see that. That time is going to make a problem. It might be good here, but it's not easy. It's not feasible there. So we are trying to have a general rule and use it for different versions. Okay. For AM alone, this can work out. You can work it out. Like, yeah, you're right, because K15 becomes a constant, so you multiply with that constant. It's okay, yeah. But the problem with this phi is that this phi is different every time. You know what is phi, right? Phi is a phase difference. Why do you think there will be a phase difference? For example, this is a generator, function generator, right? Function generator. So when I started it now, and I started it 2 seconds later, so what happened? This signal and this signal have a difference. Even though they have the same amplitude, same frequency, but they have a phase difference. That means they did not start at the same time. Alright? Next time when you do it, again there will be different phase. Make sense?
So that's why you need phase shifter.
That's why it's better to have a phase shifter. So what happens is, when the signal comes here, if you can use an algorithm to find the phase difference, which is easy, you can find the phase difference between two signals and then correct it over here. You don't have to change, you don't have to multiply and so on over here. You understand? This is all thinking, analysis, engineering, right? Okay.
Multiplying there is the easy way. It's the lazy way.
Multiplying there is an easy way, but you have to, again, it's not general. You have to change it every time. Because now, for example, due to some electronics reason, the phase changed. Then what do? Again, you have to change the amplifier gain. Right? Otherwise, whereas it is easier to solve the problem here before it propagates there. It's also something that you should learn from sensors. Remove the error as early as possible before it propagates. Right? Clear?
Yes.
Okay. Alright, so anyways, that's a good thinking. Okay, good. So this is clear, right? Because if this is clear, then everything else now will be clear. Okay, now I'm going to rub this off. Now, using the same principle, I'm going to talk about QAM, which is quadrature, amplitude, modulation. Now, remember there were three kinds of modulation. Frequency AM modulation, that means amplitude is changing. Frequency modulation, that means frequency is changing. And third one is phase modulation, where phase is changing. This one is an example of amplitude and phase, right? Modulation. Why? Because both of them are changing. When I say are changing, is whose amplitude and phase is changing?
The carrier.
Very nice. Remember, message you cannot touch. Message you cannot touch anything. You can touch the carrier. You can change the carrier based on the message, but message you cannot touch, right? Good. So now we see how it works. We have N1, we have two messages, and both of them are amplitude modulated. So this is multiplied with, say, cosine.
Suppressed carrier.
Both of them are suppressed carrier amplitude. And then this one is phase shifted. So when you phase shift cosine omega ct by pi by 2, what do you have? What is it?
Sine.
You have sine. You can do the math and then you can see it, right? It's cos A minus B. So cos A, cos B, and so on. So you have sine. Right? So this is AM1. AM1 is message 1 multiplied by cosine omega ct. This is AM2, which is M2 multiplied with sine omega ct, and both of them are added. And this is called as QAM, right? So you are changing amplitude here of the carrier, and you're changing phase here of the carrier, right? The phase is changed, right? This is why it's called QAM, right? If I ask you what is the mathematical equation of QAM? M1
the phase and the frequency.
omega ct
That's
plus
the phase.
M2
Sine. Omega ct.
simple. Make sense?
Can you repeat why do we have cosine and sine? And
Because cosine, you phase shift it
why?
by pi by 2
Okay.
to have sine,
Yes.
okay? And then that is used to multiply the second signal,
Oh, so the first signal is multiplied by cosine and the second signal is
multiplied by sine, okay? By this, the same frequency, same bandwidth is used for transmitting two signals. You see the beauty of it? You're transmitting two signals with the same bandwidth, like AM, right? Over in AM, you do not have this, okay?
Doctor, can we improve on this and send like many signals?
Then you have to have many phase shifts, and you have to make sure they don't interfere with each other. They have to be orthogonal to each other.
Of course.
This is what you have BPSK, QPSK, and all of that. This digital modulation, right? There's 16 QAM. 16 QAM. That means there are 16 phases. Okay? That's a good. I think you did not study about that yet, right? Okay. There is 64 QAM, 256 QAM. Okay. You can assume how it looks like in frequency domain, right? This signal will look, if this is FC, then there will be FC plus F1, FC minus F1, correct? This is how it looks like, right?
Yeah.
Over here, same thing, correct? So if I ask you how will this look like,
2 times, yeah.
there will be
On top of each other.
4 of them.
Okay.
This is FC, this is FC plus F1, FC plus F2, FC minus F1, FC minus F2, with the condition that F2 is bigger than, not much, F1. Okay.
Two different signals, okay.
If there are two different signals with,
if they're the same signal, then will be on top of each other.
they will be on top of each other, but how they are not interfering because of the phase. There's phase difference between them. Okay? Make sense? Good. This can be, by the way, next week you have quiz, huh? On AM and FM.
Next week,
We will do it from home. Yes.
online.
Online.
And the other group will do it here.
Yeah. There's an announcement on that.
For the Thursday at 3:30 for all of one.
For you guys it will be Tuesday. 3:30. Okay. All of this thanks and no thanks to Corona. Otherwise things were all normal. Okay. Okay, now this is modulator, right? Demodulator side. Huh? How will you demodulate an AM signal? How do you demodulate it?
Multiply by the carrier.
Multiply by the same
Same
carrier.
carrier.
So if there is cosine omega ct, say there is a phase shift. So what will you do?
Phase shifter.
You will use a phase shifter to fix the phase, and you will have cosine omega ct, right? And then this goes through a low pass filter, and then this becomes a scale M1. Same thing multiply, but this time by minus pi by 2, so that you have sine omega ct plus phi, and again there is a phase shifter here to give you sine omega ct, then that goes to a low pass filter, and this becomes a k m2. Okay? Now there can be questioned in the exam. Suppose you don't do phase shifting. Okay? So what happens over here?
The scaling will be different.
No, not only scaling will be the scale. No, not
The message will be altered.
there will be interference between message 1 and message 2. Okay? Let's prove it. Tell me what is the signal here.
M1 cosine omega ct plus
Let's go step by step. So suppose this is P. So signal at P is QAM multiplied with cosine omega ct plus phi. Right? So if you do the math, I'll let you do it at home. You will get K M1 M2 or K M1. Let me see.
So this looks like a PhD thesis.
This is nothing. This might be one of the things of. Okay, good. Over here. I want you to do it properly at home, okay? But I just summarize here. So QAM multiplied by cosine omega ct, right? QAM is what? M1 cosine plus M2 sine, right? So M1 cosine multiplied by this plus M2 sine multiplied with this. Okay? This is cos A cos B. So that means cos half cos A plus B plus cos A minus B. So that's M1 half A plus B. So 2 omega ct plus phi. A minus B, that means same cosine of minus phi. Cosine is an even function, so that's same as cosine of phi. So plus cosine of phi. Same thing happens here. Oh, I did that. Sorry. M2 over 2 sine 2 omega ct plus phi minus sine of phi. Right? So that's half M1 cosine of phi minus half M2 sine of phi plus, this is high frequency component. You know why it's high frequency component, right? Because 2 omega ct, right? 2 fc. fc is high. 2 fc is much high. So that's high frequency. That's high frequency, right? Good. So now see, over here, do I have a scaled output?
No.
You see, half M1 cosine of phi minus half M2 sine of phi. So if you cannot divide or you cannot amplify, you get the point? You see? Because this is subtraction.
We add half into sign.
So you need a phase shifter here. Okay? Because if phi is equal to 0, what happens? It becomes half m1 cosine of 0 is 1 minus half m2 sine of 0 is
0.
See? Simple.
Very simple.
Life becomes simple. Okay? This I want in the report, by the way. The reason I want it in the report is because if you get QAM in the exam, I will definitely ask this question. I want to know why a phase shifter is so important.
Regardless of using the phase shift, there still might be a phase shift due to the electronics, right?
Aha, very nice. And that's what we'll see today. So the best, and how can you fix that? It's a good question. How can you fix that?
And also phase shift is the low pass filter.
Phase shift due to low pass filter. At the end,
Yeah.
that's fine. That's phase shift will be with the message,
Yes.
not with the.
Yeah.
With the message, I can correct it, right?
Yes.
So that's fine. I can, that's a good point. But what about you? There might be phase shift due to electronics. How can you fix it?
Phase shift I cannot use, right? Phase shift I can use. Compare that message 1 and message.
So it comes down to the. Remember you always say use costly equipment, costly equipment, costly equipment. That means very pure equipment that will give you less noise or less phase shift and so on. So the more costly things you use, this is why the things in satellite and so on are very costly. Because you don't want any problems due to electronics, right? You want the best electronics there, right? Okay, that's good. Yeah. Okay, done? Okay, so this is what we'll do over here. I'll quickly show that, okay? And I will take the screenshots for you. But you can go and practice, right? Okay, done. This is QAM done. Now, BPSK is binary
Phase
phase
shifter.
shift, not shifter, keying. This is a digital modulation scheme.
This is only phase modulation, yes?
This is only phase modulation, yes. And I'll tell you, do you know why it's phase modulation?
Yes, phase changes.
The phase changes.
Yes, I saw that.
You saw the video, that's nice.
Yeah, we saw the video for this.
This one? It's
Yeah.
okay, it's clear?
Yes.
Very nice. Good. Okay, let's go. Remember, now let's do the same thing again. So now instead of continuous signal, I have ones and zeros.
101.
Whatever. 101. Okay. Now then this is changed to pulses. Who said that? Bonus.
Doctor, we watched the video, doctor.
Yeah, this is why I'm asking question. Otherwise, I was going to go straight.
Okay.
This is changed to pulses, right? Now this changing bits to pulses is called as
Line encoder.
line encoder. Line encoder. You put it there. You said that. Bonus. Everybody who watched the video will get benefits of it. Ali, I'm waiting for you. Huh?
Inshallah.
So there are various line encoders. Okay.
You use
Each.
NRZ.
Mohammed, you got the bonus. There are various line encoders. NRZ, which is non-return to zero, return to zero, bipolar 5. All of them have their own advantage and disadvantage. That's a whole new chapter. Okay, and I think Dr. Dhamar will go through that. Okay, but all of them have their advantage and disadvantage. That's a whole new lab. Today we'll just focus on non-return to zero. What it means is ones and zeros are changed to pulses that don't return to zero. So if it's a 1, it will be high.
And
If it's a 0, it will be low. So again 0, low. 1 high. So it will not return to 0. So this is 1 0 0 1. Okay? So bits are changed to pulses using line encoding, right? Good. Now the BPSK is, so now this is ready. This one is multiplied with carrier, similar to our AM, right? So now carrier is, let's assume the carrier is sine. Okay? So what's going to happen here is, when this carrier is multiplied with 1, no change in phase, right? So then, so this is 1, 1. Let us assume that the carrier is 4 times now.
4 times the time period. Of
The bit period is,
Four
for,
times.
for the simplicity, okay, you get the bonus because you remember the number 4. The bit period is 2 times the carrier period. That means what? 2 carriers make the bit. Okay? So over here, this is 1, right? So in this bit, you will have, in this bit period, so
time signal.
two periods of the
Period.
who said 2 periods? Bonus. 2 periods of the sine carrier. So 1 2.
Didn't you say it was 4?
Yeah, but drawing 4 will be, I'll mess it up. Okay, so I'm making it 2. Now when carrier multiplied with minus 1, what happens? 180 degree phase shift, right? So then instead of starting from there, it will start from here. 1
W shape.
2. It's a W shape, yes. Over here again it's a 0. So it will start from negative. So 1 2. Okay, 2 carriers, right? Over here it's multiplied with 1. So then it will start like a sine. So then it will start from here. 1 2.
M shape.
Aha, very nice. Can you see this? W M. So I have good M's and W's which shows phase shifts, right? And what I did, I just multiplied. So it's AM but with digital signal. At the end you don't have this. Okay, you will have your carrier, and the phase shift of the carrier denotes the pulses or the bits that is transmitted. Okay, but the trick is, if you want good M and good W, you have to make sure that the bit period is large or a whole number multiply of the carrier.
Does it make a difference if it's 2 or 4?
No, it doesn't make. But obviously, that's a very good question. You want carrier to be very large, right? Because you want it to have good amount of energy to go longer distance. So the higher the carrier, the better it is. Okay? Clear? Good. This is. See, I told you, everything is now AM. Okay? Now, let's go to demodulator side. The ones who said, please, now let others focus. Huh? Now, if I want to demodulate, what should I do? Multiply by carrier. Bonus. So you multiply by carrier, right? But what is the trick?
Same carrier.
Same carrier. What do you do after that? Low pass. Bonus. Okay? Who did not get bonus yet? Sam. Shabana, what happened?
I'm okay.
You're okay, huh? Life is okay. Don't need a complication, huh? Ayat?
Yes.
Okay.
Yeah.
It's okay, huh? He's still thinking of being a lawyer. But life is not that simple. How can it be same?
Engineers complicated.
Engineer makes complication easy.
Allah.
Yes, sorry.
Yeah. Over here, why is it not going to give back my message? What is my message?
It is pulses, square pulses.
Okay.
So low pass filter will take off the high frequency component and
This is beauty. This is Jamila thing. Very nice. You see here, low pass filter is what? Removing high frequency, right? Square wave. Square wave has infinite harmonics, right? So you will never get your square wave back. You will have like this, right? This is not what you transmitted, right?
Okay.
What you do after this is you use another block,
Decision maker.
decision maker, very nice. So that you take decisions at points, right? Whenever at this point it's high, that means it's high. If it is low, it's low. High, high. So now this harmonic is made proper. It's like an if condition here. If more than this, output is 1. Less and so on, right? Now you got your pulses. What did you transmit in the beginning? What are you transmitting? Bits.
Yeah, bits, yeah.
So what do you need to do over here?
Decoder.
Decoder. Which decoder? The same decoder that you did. And what will you get back? Bits.
1001.
1 0 0 and 1. See? So BPSK is nothing but AM with digital concepts, right? Okay. One important problem that all of you will face is bit clock and master clock. You use same bit clock throughout. Okay? And you get bit clock from
Line encoded.
master clock. Yeah, you get the bit clock from the line encoder. Master clock gives you your bit clock and use it on all digital modules. Can you tell me what are the digital modules?
The decoder.
Line encoder, line
Line
decoder,
encoder.
decision maker. Okay? Clear? Understood?
Master clock, you mean the line encoded.
The master clock, I mean, I remember the carrier. The carrier will be used to give the bit clock. Okay? So I just multiply 2 times to give. That's very good. Let me write it over here. Master clock is like the carrier. Bit clock is.
Doctor, do we put it on the system like
Yeah, I'll show you how to do it. Okay? Done? Ready?
Yeah.
Okay, come this side. Let's see QAM here and then we'll see.